Welcome to Satellite Communication course. Today we start here a GPS satellite transmitter. So we say that a GPS satellite transmitter transmits a data, that navigational data at 50 bits per second, and that data consists of a satellite time and a synchronization signal. Now, as we say that that data contains, we say that a satellite timing, then we say that a sync signal that is related to whatever the timing and all. Then along with that orbital data of a satellite, that we say that ephemeris. And again we say that a orbital data of other satellite. That is the information we required, and what will be the signal transit delay, then a correction information for satellite time, then we say that a signal transit delay, along with that a correction information for the satellite time, then a data on ionosphere, and telemetry data of the satellite. So now that is about, we can say, a satellite data that will be transmitted from the satellite, and the data has a message of whatever the data message, it is of a 37500, that is bits, and that bits required a timing of 12.5 minutes. That is about a time of a transmission, and that rate at a 50 bits per second. And that is about this message transmitted from the satellite, and then that message transmitted from the satellite that will enable the GPS receiver, and then it will compute the position of the satellite and a time of a transmission there. So now that is about a data. That data is a low speed data that are transmitted using a speed spectrum modulation by a modulo to addition with a pseudo random code, and that pseudo random code at a PN code that will be at a 1.023 megabits per second. And this particular PN code, generally we can say that a ranging code. This is about a PN code, we say that ranging code, and we say that a BPSK modulation takes place and then we can say that a modulation of that GPS key modulation of L1 carrier, or we can say that in a modulation in a L1 L band there. So now if you see here that code of a 1.0 1.023 megabits per second means you can say that that is about a 1.1023 bits and with a chip rate of 1.023 megahertz, and that code is transmitted and that code is repeated. It will repeat at every 1 millisecond period, and that particular PN code generally we can say that a signature code for the satellite, and it is different for the different satellite, and then receiver identify that transmitted code from the satellite, and then or we can say that that navigation message that will be received by this receiver, and then according to that they can identify the position there. Now we see that what is the or what are the various components of a GPS satellite transmitter. So if you see that a GPS satellite transmitter that transmits that a two carrier, that is about a L1 carrier and a L2 carrier. Now that L1 carrier, if you see that that L1 carrier is generated by a automatic clock, that automatic clock it is available on board on the satellite there. So that generally we can say that a satellite has a onboard clock of a 10.23 megahertz. That is about the onboard clock, and that on using that onboard clock it will generate a two carrier signals, and the two carrier signals are called as a L1 carriers and a L2 carrier. This is about a GPS transmitter block here, and it's just like if you consider that this is about a 10.23 megahertz, that is about the clock, so it will generate the L1 carrier, and that L1 channel is generated or L1 frequency is generated by multiplying the fundamental frequency with 154. Okay, means this is about a 1.10.23 megahertz is a fundamental frequency, and that fundamental frequency, okay, it will be multiplying the fundamental frequency by this 154 value. So then it will generate that L1 carrier. Similarly, if you consider that L2 carrier, that L2 carrier is generated by multiplying this fundamental frequency to this 120. Then this L1 and L2 carriers are generated. Now that transmitter, GPS transmitter transmit that two carriers that are L1 and a L2 carrier, and that L1 and L2 carriers are modulated with ranging codes with a modulo to addition with the GPS message. Okay, now we can say that we have a modulo to adder, and then that will be transmitted. So if you see that ranging code, there are the three types of ranging codes that we can say that a C by A code, P code, and a Y code. So that ranging. Now we say that we have this ranging code, and that ranging code we say that C by A code, P code, and a Y code there. That C by A code is generally a course acquisition code, and that code is released to the general public. And if you consider that a P code, that P code is available only for the military and some authorized person. Now, this C by A code, if you consider that a C by A code, that is about a C by A code, how it is generated. That C by A code has a chip rate of 1.023 MCS. That is about a chip rate. And it has a 1023 length. Okay, that is about, we can say that a length. This one is about a rate here. We can say that it's about a length. And it will repeats at every 1 millisecond. And that particular code, if you consider, that code has an ID for the satellite. Means it has a ID for satellite, and that ID generated for this particular satellite, that will be different for each satellite. Okay, so means C by A code generated, that code has some particular ID, and that ID is different for each and every satellite. And then we can say that the C by A code, generally we can say that this code is nothing but a gold code, and that gold codes are used for this purpose, and that is gold codes are generated by the modulo 2 addition. Okay, now you can see that this one is about a C by A code here. That is a C by A code, or we can say that C by A code is nothing but a gold sequence, or we can say that C by A code is nothing but a gold code there. And that gold code, that C by A codes are not, for satellites are nothing but a gold code here, and they are produced by this. What will be the sequence? That is about, we can say that a PRN code using the generator G1 and a G2 generator. These are the two generators, G1 generator and a G2 generator here. And through that gold codes are generated. Now, if you consider that G1 and a G2, that are a code generated by that is a shift register. This is about a shift register of a 10 stage. Now you can see that 3 and 10 is used for generating this G1 code. And here we can say that 3 and 8 is used for generating this G2 code. Now we can generate that a code, that's C by A code, and that if you consider that equation for this G1 here, G1 code. So G1 code is nothing but what? If we consider in terms of a polynomial, and that shift registers of each and every stage, that is about its 10 stage. And if you consider that that shift registers are set to all one state, and that are synchronized with the x1 epo, then you can say that g1 of x is equal to 1 plus x raised to 3 plus x raised to 10. That is about a 3 here and a 10 here. So x, so that is about a g1 here. And that g2 is nothing but what? That is a polynomial we have considered, and that is a addition of what? There is a 2, 3. Okay, then we have 8 here, we have 9. Okay, so we forgot to add here 9, then a 10 here. So that way we can generate that a G2 code. Means if we write a G2 of x, so that will be what? 1 plus These are the taps, okay, at this particular place. So x3, x6 plus x raised to 8 plus x raised to 9 plus x raised to 10. Okay, that is about a G2 code. So means overall C by A code is generated, that is multiplication of this G1 and G2 code there with with a factor of what we can say that is some phase offset of these chips with respect to that a G1 and G2 code. So that is about a C by A code generation. And that C by A code generated, that modulates, that C by A code generator, and that modulates only to the L1 carrier. Okay, now this one is about a C by A code generator. This one is about a L1 carrier. Okay, and this C by A code generator will modulate only to the L1 carrier. And that is about a for this a code polynomial for this G1 and G2, we can write here G1 of x is equal to x cube and x raised to 10, and this is about a G2 polynomial. So that's why the both the codes are generated, that G1 and G2, using the 10-bit feedback shift register. And that feedback shift register with the feedback tabs, and that feedback tabs are this what with respect to the polynomial. So polynomial means 3 x raised to 3 and x raised to 10 means 3 and 10. That's about a tab. And then we can say that G1 code is generated by a modulo to addition of output 3 and a output 10 here. Output 3 and a output 10 here. So that is about, we can say that if shift register is connected, that is about for this particular feedback is connected at the first input stage here. Okay, means after that it will be connected back to the first stage here. So that is about your a C by A code generator, and that C by A code is nothing but it is called as a gold code. Now next another code is about, we can say, a P code. Now we can say that a P code, if you see that a P code is have, it has a P code. Now now we can say that a P code here. Now for the P code, so that P code is available only through the military code and a authorized person, and it has a chip rate of 10.23 MCS. And that if you consider compare with the C by A code, then that P code, it has a 10 times higher than this, that C by A code. So now you can see that this is about a C by A code. So C by A code is about 1.023 MCS here, and if you compare that a P code, that is about a 10.23. So if you consider that in terms of rate as well as in terms of accuracy, so this P code is 10 times higher accuracy or higher accurate than this C by A code. And this P code, it has a period of it has a period of 7 days at its high chip rate. So generally we say that if this code is repeated after every 1 millisecond, but in the case of P code, so that P code is nothing but what we can say that it has a period of a 7 days, and P code is generated by modulo to addition. Okay, now we can say that we have this a C by A code generator, and we can say that a P code is generated by the modulo to addition of this x1 and x2 with the length of what, that is 15, 3, 4, 5, 00, that is chips, and 15 34 50 37 chips. Okay, these are modulo to addition, and then it will generate that a P code. This is about X1, and this one is about a AX2 here. Now that a code, we say that a modularity added, and that will generate a P code here, we say, and then X1 and X2 are just like modularity addition of that whatever the delay code there. Okay. Now, if you see that this one is about a L1 signal and a L2 signal generated for this a GPS transmitter. So means we can say that is whatever that navigation data to be uploaded from this from this control segment for this GPS transmitter. So that is about a data is transmitted with a BPSK modulation. Then a satellite receives that navigation data that are uploaded from this control station. That is nothing but a control station send the data on this TTC command. Okay, telemetry tracking and command channel. So that is about TTC, and it has a data of what we can say that this data is about what a 50 bps data, and that are modulated on this PN code at a 1.023 MCS with a modulo 2 adder. And then this is about a modulo 2 adder here, and then that sequence, what will be the sequence, that sequence is added with this L1 carrier. You okay, so we can say that we have a spectrum of this that will be added with the L1 carrier, and we'll get that a modulated BPSK modulated output, and that will be transmitted. Now if we consider that a BPSK carrier here, that BPSK carrier is about what a 1575.42 megahertz, and that is obtained by this multiplying this clock with a 154. So that is about your satellite transmitting the data there. Now if we see here in this particular figure, we say that a L1 carrier is there, means we have the C by A code, and then we can say that is about a P code here. But how this is C, that how this L1 and L2 carriers are generated? That L1 and L2 carriers are generated using multiplying this atomic clock, multiplying this atomic clock, and then it will generate that a L1 and a L2 signal. Now that L1 and L2 signal, if you see that L1 and L2 signals are transmitted, and that signals are received by the Earth station, and that L1 signal consists of a data. Okay, now if you see that it has a L1 carrier, it has a C by A code. Okay, so means it has a navigational data. Okay, so we have this NAV data. Okay, so now we can say that it has a navigational data. We can say that a L1 signal has a data L1 signal, it has a P data, it has a C by A code. Okay, it has a navigational data. So that all these are combined here, and that will be transmitted. Similarly, at the L2, so if you consider that L2 signal is obtained using that L2 carrier, plus we have this P code. This is about a P code here, plus navigational data. Okay, That is about a nav data. How it is? Now you can say that P code navigational data here it is added. This is nothing but a modulo to adder, that navigation data of 50 bps plus P code both are added here, and that are combined to this L2. So that's why L2 signal is what? What you can say that L2 carrier plus your P code here plus navigational data. That is about L2. And that L1 carrier is what? It has what? A L1 signal plus P code plus navigational data plus C by A code. Okay. So means P code, navigational data, C by A code, both are added here and that are mixed. So here it is all the signals are combined. So we can get the L1 carrier plus P plus C by A code plus navigational data. That is about a L1 signal. Now if we see the typical spectral pattern of a GPS receiver signal, the GPS receiving that L1 signal. So if you see the spectrum here, okay, so spectrum contains that is about a L1 signal. So it has okay. So now this is nothing but what we can say that a L1 signal that is about 20.46 megahertz. But if you consider that in terms of a carrier, we say that 1575.42 megahertz. Okay, and this is nothing but what we can say. This one is nothing but a C by A code, and this is nothing but we can say that a P code here. And here it has a 2.046 megahertz. Now, if you see this particular power spectrum here,